Hello everybody, appreciate you joining me again. On today's lesson we're going to learn a little bit more about additional techniques or methods that we can use to attempt to measure the shear strength of the soil. And in particular in this lesson we're going to be talking about methods that are more common with fine-grained soils, so clays and silts. And we're going to be talking a little bit about a technique called or measuring the undrained shear strength of samples. So in lesson 20 we talked about two different types of tests that are performed in a triaxial shear device. We talked about the consolidated-drained test, where if you recall in a triaxial test there are two stages. In the first stage, in the consolidated drain test, we leave the drains to the soil open so that when we apply the cell pressure in the triaxial apparatus, the soil can squeeze all of the water out of it and the soil can compact or consolidate under the pressure that we're applying. And then in stage 2, for the drained portion of the test, we leave the drains open and we shear the soil sample slow enough so that there are no pore pressure effects while we're shearing the soil sample. So in this test, the CD test gives us a drained shear strength properties of the soil, or sometimes we call them the effective stress shear strength properties of the soil. The next test that we talked about is the consolidated-undrained triaxial test, where it's similar to the CD test in the first stage, where we allow the soil to consolidate, but in the second stage we close the drains before we begin shearing the soil, and in doing so we do not allow the volume of the soil to change. We don't allow any water to leave the soil, and we do not allow any water to come into the soil. As a result, pore pressure effects will build up in the soil as we're shearing it, but we're measuring those pore pressures. And so we can obtain from the CU test an undrained shear strength of the soil as well as a drained shear strength of the soil. So each of these tests involves consolidating the sample under the cell pressure sigma 3 before we shear it. But here's an interesting conceptual question for you to consider. What would happen to the pore pressure and the effective stress in the soil if we close the drains before we apply the cell pressure? So at the beginning of stage 1. So in doing that, we're not going to allow any consolidation, and then we start shearing the soil immediately. So in this particular instance, think back to the analogy we made with soil consolidation, where if I have a piston that maybe looks like this in a cross section and it's filled with water, you get the idea. And then it has a spring inside of it. If I apply some stress to that piston, if there's no way for the water to get out, the stress that's applied is simply taken by the pore pressure. And the spring itself feels no effects from the load that we apply. The only time the spring will feel those effects is if we have a drain and we allow the water to drip out of the chamber. And if that happens, then the piston is able to go down, and as that piston goes down, it will compress the spring, and the spring will then fill the change in stress. So if that rings a bell, that's what we talked about in consolidation. It's the same principles, though. If we're talking about this in terms of consolidation and shearing in a triaxial device, if the piston can't release the water and there's nowhere for the water to go, then the water is going to take all of the load that is applied to it, whether it's from the cell or whether it's from the piston. So as a result, the soil can't consolidate because there's no way for it to get out of. or there's no way for the water to exit the soil. So if the water in the voids then takes all of the cell pressure, and in addition to that, takes all of the pressure from the loading ram of the triaxial device, what we might ask the question, what is the actual effective stress in the soil? And the truth is we don't really know what it is. It's whatever the effective stress was at the moment we closed the drains to the soil. Whatever that stress was, the moment we closed the drains, we locked that effective stress into the soil, and there's no way for us to actually measure it. So when we close the drains at the beginning of stage 1, this is what we call a UU, or an unconsolidated-undrained triaxial shear test. With the UU test, the deviator stress that we apply to the soil from the ram is at failure is always going to be the same, regardless of what cell pressure we apply to the beginning of the stress. So in other words, if I take a soil sample, let's say I take three identical soil samples that had the same effective stress in the ground, and I put them in a triaxial device, and I close the drains at the beginning of the test, and I apply cell pressure of this value for the first one, and this value for the second one, and this value for the third test. It does not matter what cell pressure I apply, I get the same circle. That deviator stress, actually it is a sigma D. That deviator stress is the same regardless of the initial cell pressure. And that's because we locked our effective stress in when we close the drains. The soil doesn't even feel the changes that we're applying to the cell pressure. The soil just feels the stress that we locked into it. So because of this, if we perform multiple tests and we draw the failure envelope tangent to all of these failure circles, what we see is that that failure envelope has a friction angle equal to 0. It's a horizontal failure envelope. That implies then, if I look at my Moore-Coulomb equation, where shear strength is a function of cohesion and it's a function of friction, that implies that if phi equals 0, then my tangent of phi also equals 0. And that means then that there's basically no friction in the soil. At least that's what the method tells us. We know that's not true in real life, but that's what the method is telling us. So that means that all of the shear strength of the soil comes from the cohesion. When the tangent, or when the friction angle is equal to 0, this is a special case of loading that we call undrained shear. And then we define the cohesion as either C sub U, that's the undrained cohesion, or we define it as S sub U, which is called the undrained shear strength. These two terms mean the same thing. They're synonymous. So the UU test is really trying to simulate the soil immediately after a load has been applied, but before the soil has had an opportunity to consolidate under that load. So in order for that simulation to be true, two critical assumptions need to be met with the UU triaxial test. First, we're going to assume that the existing effective stress that's in the soil the moment we close the drains is going to be the same effective stress that the soil was experiencing in the ground. So in other words, from the moment we pulled it out of the ground to the moment we closed the drains in the triaxial device, the effective stress that the soil was feeling did not change. That's an assumption that we make. The second assumption is that the soil is completely saturated. Now, these two assumptions are only true if we can find, retrieve, and place a completely undisturbed and saturated soil sample into the membrane and triaxial device. Here's the truth of that. That's not going to happen. It's impossible. Anytime we sample the soil, transport it, extract it from the ground, or get it ready for the test, we're going to disturb the soil in one degree or another. And so because of that, these two assumptions that we're making aren't necessarily true. So the real issue is what's going to happen because those assumptions aren't true. Well, generally, it's going to reduce the undrained shear strength because we're weakening the soil by disturbing it. So we're going to usually measure a lower undrained shear strength than what is actually existing in the ground. But this isn't necessarily a bad thing. A lot of engineers like this. They think, oh, cool. So if I use the undrained shear strength and from this test, and it's lower than what it is in the ground, then that is conservative, and I'm being safe in my designs. But that leads us to an interesting test, or a version, I guess, of an undrained shear test. If we look at the UU test, let me go back a couple slides. If I look at this test here and I see these three different circles, and it does not matter what the initial cell pressure was, then what's stopping me from saying, well, why don't we just make the initial cell pressure 0 and put our circle there? Well, okay, theoretically we should be able to do that. So if the initial cell pressure is 0, that just means that there's nothing confining our soil sample. It is exposed to open air. So this type of test has its own name. We call it the unconfined compression test. And in the unconfined compression test, because there is no confinement, we say that sigma 1 at the end of the test is what we call the unconfined compressive strength. It has its own term or its own name. We call it Q sub U. And thus, because Q sub U is really equal to the deviator stress in the test, then we say that the cohesion of our soil, C sub U, or the undrained shear strength, S sub U, is just going to equal the unconfined compressive strength divided by 2, which is the same as saying it's the deviator stress divided by 2. Okay, well, this looks great. It looks like an easy test. It looks like it would be quick to run, and it is, and things look peachy. The problem is with these assumptions. Okay, these assumptions are always assumed to be met when we do these undrained tests. The problem with the unconfined compression test is that we're not even close to meeting them. Because there's no confinement around the soil, moisture is free to leave the soil as it wants to. Not only that, but we can expect a lot of other effects to happen, such as unraveling or lack of confinement. And because of that, we're going to see something interesting. We see that the undrained shear strength that we measure from an unconfined compression test is always lower than the undrained shear strength from the same soil if we were to measure it in an unconsolidated-undrained triaxial test. And again, the reason for this is because the soil isn't truly saturated. There's more sample disturbance, there's lack of confinement, and we'd have the potential for the soil to unravel. So my final opinion of the uncompression test is that it's garbage. I do not like the unconfined compression test at all, and I am frankly surprised that it gives us anything even remotely close to good data. I would rather, if I want to get the unconsolidated undrained shear strength of the soil, I would rather recommend a UU triaxial test to obtain that. Now, there's other methods that we can use to estimate or measure the undrained shear strength of the soil. One method that's really popular with geotechnical engineers is what we call S sub U over sigma prime methods. Sometimes these are called C over P methods. That comes from Great Britain. It's basically the same thing. Researchers such as Skempton have discovered or found that the ratio of the undrained shear strength of the soil to its effective stress in the ground is essentially a straight line. And they found that it correlates well with the soil's plasticity index. And so as a result, they've developed these empirical correlations that allow us to approximate or estimate that ratio. With that ratio, all I need to do is multiply the ratio by the computed effective stress of the soil, and I can come up with an estimate of the undrained shear strength of that soil. Now, this relationship from Skempton is specifically for normally consolidated soil. If I have over-consolidated soil, then I can use this relationship shown below, which has an additional term for the overconsolidation ratio. So it's going to increase our ratio of shear strength over effective stress slightly. There's some other methods that we can use that I like to refer to as quick and dirty methods. So one of these methods is called a Tor vane. So a Tor vane is a little handheld spring device that allows you, when you press it into the clay and you spin it, you can get a rough estimate of the undrained shear strength. If I click on this little YouTube video here, it can demonstrate what that looks like. We're patiently waiting for the internet here. Well, we'll see if it starts playing in a second. So this handheld spring we twist in the clay, and the amount of twist or torque that we can apply to it is going to correlate directly to the undrained shear strength. Another device that we can use that's similar to a Tor vane is called a pocket penetrometer. This is another handheld device. It's a little spring device, but this time it looks like a pen, and we can push it into the clay and get a rough estimate of the unconfined compressive strength. So I wonder if this video is going to work any better. Let's see. There we go. Here's the Tor vane. So the Tor vane, you can see it's just a spring with a scale on the top of it, and it has some paddles on the bottom of it. And you get a sample of your clay, you push the paddles down into the clay like so, and then you simply turn it until it pops like that. And then you look at whatever the little red dial is pointing to, and that correlates to the undrained shear strength of your clay. Let's go back to the presentation here. Let's see if we can get the other one to work. Well, you know what? It's just not working. Oh, there it is. There it is. That's the pocket penetrometer. So you see it's a pen. It has a spring inside it. There's a little line that you can faintly see that he pushes the probe in until he reaches that line, and then the little red slider slides on a scale, and we correlate that directly with the unconfined compressive strength of the soil. So those are the Vane and the pocket penetrometer. Now these quick and dirty methods are just that. They're quick and they're dirty. I do not recommend that these ever be used for actual engineering design. Rather, they're more as indicators or just quick checks to get an idea of what the shear strength might be in the soil. A lot of engineers want to rely on in situ field methods, so measuring the shear strength directly from the ground. One way we can do that is using empirical correlations with in situ tests such as the standard penetration test that we spoke about in an earlier lecture, or the cone penetration test, also known as the CPT, and there's other tests that we can perform. Now when we correlate penetration resistance in the soil to undrained shear strength, there definitely is a correlation, but there's a lot of scatter, tons of scatter, meaning that if I were to plot, for instance, if I were to take, say, SPT resistance, we often call this the N value, and plot that against the undrained cohesion of the soil, we would generally see a trend that might look like, this. So there's definitely a correlation there, and researchers come and they fit lines to the data. But what we need to consider is that if I look at any given N value, like N star, this value right here may be my mean undrained shear strength, but if I were to look at the spread of the data, I would see that there is a probability distribution that I need to consider. So there's possibility that my shear strength could be higher. There's possibility that my shear strength could be lower. So when we have scatter in our data, we need to consider that in our designs. Another method that's really popular in certain places of the world, like in Canada and Scandinavia, is the Vane shear test, or the VST. The Vane shear test is a really handy device. Basically, it's a paddle-like probe with 4 paddles that is lowered down into a borehole and pushed down into the soil to the depth of interest, and then it is spun up at the top, which the torque goes all the way down and it spins these paddles, and you measure the torque that's applied to spin the paddles in the soil. And so what that will do is, if I draw a plot here, and let's say that I draw torque, I'll call it gamma for strain, and then I plot T for torque. What I may see that as I turn it and strain it, I'm going to get a peak resistance typically, and then at larger strains it's going to give me some sort of residual. So we might call this T max, the maximum torque, and then we might call this T residual or T res. That means it's the residual or the long term strength of the soil, usually associated with what we call the critical state of the soil. So we can use this measured torque to obtain an estimate of the undrained shear strength of the soil, and it's a function of the geometry of the vane. So we have the width of the vane is D, the height of the vane is H. That's these terms here in the equation, and then of course the T is the torque that we measure on the vane itself. Now, if we're measuring the maximum torque, then we stick maximum torque down into this equation. If I want to get rid of that and instead put the residual strength in, that's great. But then what we're doing is we're measuring the undrained strength for the residual instead of the peak undrained shear strength. So this is something we have to consider, whatever we're using. Now, a Scandinavian researcher, Bjerrum in 1974 published a paper, and he showed that the plasticity of a clay can impact the shear strength that you measure with this Vane shear device. And so he proposed a correction factor, lambda, that is a function of the plasticity index that we compute from the Atterberg limits. So we can correct our undrained shear strength measurements, and generally what we see is we can get estimated strengths or increased strengths of on the order of 30% for really low plasticity clays. For high plasticity clays, it will actually reduce the measured shear strength slightly, maybe up to if you get really high plasticity clays, you can get like a 10 to 30% reduction. But anyway, this is a nice factor that is commonly used in practice. So here we are. We've talked a lot about soil shear strength. And we've introduced the concept of drained shear strength and undrained shear strength. We're going to use drained shear strength when we want to look at the long-term or the steady-state stress conditions of the soil, when there are no more excess pore pressures in the soil from shear stress or shear loading. To measure these drain properties, we can get them from a direct shear test, from a consolidated drain triax test, or from a consolidated undrained triaxial test after we've corrected the data for the measured pore pressures. In terms of shear stresses that are computed, the shear strength of the soil is just a function using the Moore-Coulomb equation of cohesion and friction. But we're just going to make sure that we put in the drained shear strength parameters from those tests. This is the typical envelope that we use for cohesionless soils, and again, any soil where we're looking at long-term or steady-state stress conditions. The alternative to the drained is the undrained failure envelope. And the undrained failure envelope, we do not need to know what the pore pressure is because everything is based on total stresses, not effective stresses. So we're going to assume that the pore pressure that's generated in the lab is the same that's in the field. Therefore, I don't really care what it is. It just happens. I'm just going to measure the shear strength of the soil and assume that that's the same shear strength I get in the field. So we measure phi and c. This is also equal to phi sub t that we saw in previous lectures. This phi and this cohesion c we usually get from a consolidated undrained triaxial test if we want to initially consolidate the soil. If we want to account for the condition where no consolidation occurs, in other words, immediately after a load is applied, then we're going to assume that phi equals 0. And then we have to come up with an estimate of the undrained cohesion, and we can get that from an unconsolidated undrained triaxial test, a Vane shear test, an unconfined compression test, though I recommend you don't use that method, or any of the other methods we discussed, like S sub u over sigma prime v, and any of the other methods. Now this method is much more typical for cohesive soils. So especially like normally consolidated clays or silts, to look at instantaneous loading conditions right after the load is applied. So a lot of students, when they're exposed to the concept of soil shear strength for the first time, get really confused because they say, how do I know which failure envelope I should design for? Should I design my soil for the shear strengths that are drained, or should I design them for shear strengths that are undrained? And the truth is, it may have to be both, because soils can behave both drained and undrained just depending on the conditions. So I've put a lot of thought into this question, and I've developed a tool that I hope will be useful to you. It's a flowchart that will help guide you to which failure envelope you may want to use for design or evaluation of the shear strength of the soil. So basically you start here and you just work your way down through the different questions. And you'll see that there are different stages or different questions. The first question has to deal with whether the soil consolidated under the applied load. The next questions have to do with, is there any additional loads that are applied after the soil is consolidated? And you'll also see a lot of questions like, does the soil dilate or contract when you shear it? So rather than, you guys can sit and study this and look at it and follow all the steps, and that's great. I recommend that you do that. But I just recommend that we maybe look at some examples of how to use this chart, and then I think you'll see why or how it's useful. So let's look at the condition of a brand new footing that is being constructed on loose sand. And because it's loose, the soil tends to be contractive. And it's unsaturated. We're above the water table. And we want to know which shear strength parameter should we use. Should we use the drained shear strength parameters, or should we use the undrained shear strength parameters? Now the answer to this may seem obvious because we're above the water table, so of course we're going to use the drained parameters. But let's show how this flowchart might be useful to solve a problem like this, or to answer this question. So we're going to start, and we're going to go down to the first question. Has the soil fully consolidated under the applied loads? Well, whenever we apply a load to a coarse-grained soil like a sand or a gravel, it drains immediately, and so as a result it consolidates and experiences settlement immediately. That's why we call it elastic or immediate settlement. Therefore, we say as soon as the load is applied, if the soil is sand, it's definitely already consolidated under the applied load. So if that's the case, then we can see that the induced stresses have already fully transferred to the soil matrix, and there's no excess pore pressures existing in the soil from the load that has been applied. As a result, the effective stresses are increased, and because shear strength of the soil is a function of the effective stress, if effective stress increases, then shear stress increases as well. Okay, so the next question now. Is a new shear stress applied to the soil from some other source, like an earthquake or a rapid drawdown of a dam or a levee or something like that? Well, in this case, no. It's just a footing. The footing is still sitting there. There's no new footing being applied on top of the old footing. It's just a footing. So the answer to that would be no. Therefore, following the flowchart, we can see that for this problem, we're going to design with the long-term shear strengths. We're going to use the drained failure envelope. To get the drained failure envelope, we can use a direct shear test, a CD triax, or a CU triax with pore pressure corrections. That's how we would obtain those values for design. Cool. It's easy, right? So why don't we practice with one more, maybe a little more challenging problem. Let's say now that we have an existing, and I want to emphasize the word existing, dam that is suddenly shaken and sheared by an earthquake. The dam is founded on a dilative silt layer. So we want to know the shear strength of that silt layer, just in case we can see this failure surface coming through the dam and down into that silt layer. We may want to know what the shear strength of that silt is. So which failure envelope would we use for this case? Let's use our flowchart. So again, we start. Has the soil fully consolidated under the applied loads? Well, in this instance, what is the applied load on top of the silt? Well, it's the dam. Okay, well, if the dam is existing, it's been sitting there for a long time, which means the pore pressures have had chance to equilibrate, and any excess pore water pressures that may have been induced in the silt have long ago dissipated because the dam has been there for a long time. So yeah, the silt has consolidated under the presence of the dam. So now the next question, is a new shear stress applied to the soil from some other source, such as an earthquake or rapid drawdown? Well, in this instance, yes. The problem described an earthquake that was hitting the dam. So the earthquake is inducing a new shear stress into the soil after the soil had already consolidated from the dam. Therefore, the answer is yes. There is a new shear stress being introduced into the soil. So the next question, do we know the excess pore pressure that's generated from this new induced shear stress? And the answer is no. I have no idea what the pore pressures are going to be in that silt from the earthquake. Okay, so the next question and the final question, does the soil want to dilate or contract when it's sheared? The problem told us that the silt was dilative, and as a result, we can see that negative excess pore pressures from dilation will tend to increase the undrained strength in the short term. But in the long term, those undrained strengths that were temporarily increased are going to dissipate. The strengths are going to come back down because the soil will lose the vacuum effect and will equilibrate, and we won't have any more excess pore pressures in the long run. So what we want to do then is we want to check both the drained envelope and the undrained envelope with the initial consolidation from the dam. And then whatever two of those shear strengths is lower is the one that we want to design for. So hopefully you can see from this flowchart how we might make the decision-making process in selecting which failure envelope we're going to use for design. Please keep in mind that laboratory shear strength tests are nothing more than simulations of what is going on in the field. And so when you try to go through this flowchart, try to picture, what should I be doing to represent the loading scheme and what the soil is doing in the field. And I think that will help make sense of the flowchart a little bit better. So thank you for watching this lesson. I look forward to giving you the next lesson, which will talk a little bit more about some of the what we call stress paths in soil, and it will also talk about what we call quick clays or very sensitive clays. Very interesting lesson. So have a wonderful day, and I will talk to you next time.